I think we can begin the recording. Okay, welcome to the Graduate Online Combinatorics Colloquium. Today, I'm very excited to introduce Claudia Yon, who's going to talk about homology representations of compactified configurations on graphs. Before she starts, let me just go over the 3 ground rules of the seminar. So number 1, we're all learning. Number 2, everyone has something to contribute. And number 3, no one has all the answers. And Claudia has already said that if we have questions, we should interrupt her. So I'll be monitoring the chat, but I think it sounds like it's okay if you unmute yourself. Would you agree, Claudia?
Yeah.
Okay, awesome. Course. All right, take it away.
Great. Thank you so much, Sarah, for the introduction. And I really like the ground rules. I think every seminar should do that. So today I'll be talking about homology representations of compactified configurations on graphs. It's a mouthful. And I'll quickly go through the outline just because it's gonna feel a little bit discontinuous at some point, because even though I'm talking about configuration spaces, I will actually start with a discussion on tropical geometry, because it's our motivation of how we got to configuration spaces. So I'll say a few general things about this particular tropical moduli space, ΔGN, and I'll tell you how it's connected to configuration spaces in general. And then once we establish this connection, I'm going to tell you more about how we computed the homology of these compactified configuration spaces through a cellular decomposition. And I'll say more about the various group actions we have on this cellular chain. And so first of all, I'm just gonna start with a quick general description of tropical curves. I'm not going to give you any technical details or specific definitions, because I think it's good to have an intuition, and you don't really need any tropical geometry really. And so tropical curves are, generally speaking, vertex weighted connected metric graphs, and they can be multi-graphs, which means you can have self loops and multiple edges. And they could also possibly have labeled rays on their vertices to represent marked points. So here I've given you some examples of what tropical curves could look like. I did not mark any edge lengths, but these edges, potentially, they could have different real values on them. And you can see here, we have these vertices that are weighted. And in fact, none of these tropical curves have a marked point. And so we don't see any rays here. And the tropical moduli space, which we denote by ΔGN, as a topological space, it parameterizes isomorphism classes of these metric graphs with genus G and N marked points. And furthermore, we require all these metric graphs being parameterized to have total edge length 1. And how we define the genus of a tropical curve is by first looking at the genus of the graph itself. And so that's the first Betti number of the graph. And then we're going to add to that first Betti number the total number of vertex weights. And so if you look at all these tropical curves I've listed here, they all have genus 2, because these 3, they have first Betti number 2, and they have no vertex weight. And these 2, they have first Betti number 1, but they each have total vertex weight 1. And so we're going to add the 2, and then we're going to get genus 2. And we impose this total edge length 1 condition so that we get a more interesting structure. And you can also see how, if we are just looking at this first graph here, so imagine we allow the 3 edges to vary in length, then and if we require the total edge length is 1, then we can already see that it's parameterized by the interior of a 2 simplex. because we're asking, okay, give me 3 real values, non-positive real values that add up to 1. And so in general, delta GN as a topological space has the structure of something very similar to a delta complex, where each of your combinatorial graph giving the interior of some simplex, depending on the number of edges in your graph. And then we're gluing all these simplices together. However, it's not exactly a delta complex because we have this term isomorphism classes here. So since it's parameterizing isomorphism classes, we might have some weird self-identifications on these simplices. But for now, you can sort of just think of delta GN as a delta complex, but some simplices might be glued to itself.
A quick question.
Yes.
Could you remind me of what makes something a metric graph? I think I got it in the explanation.
Yeah, sorry. Yes, so a metric graph, I guess in my opinion, is a graph with an edge length function. So you assign a positive real number to every edge, and then you're sort of thinking, oh, it's not just a combinatorial graph, but every edge actually has some length to it. So I think that's the definition of a metric graph. But that's what I'm talking about when I'm saying metric graphs.
Okay.
Okay, thank you so much for asking. Okay, so now we sort of know, okay, what this delta GN is about, but why do we care about it? Well, it's actually a really cool space, surprisingly, because it has been identified with many other cool spaces in math. For example, it's been identified with the boundary complex of the Dillon-Mumford compactification of the the algebraic moduli space of smooth curves of genus G with unmarked points. And that's MGN here. And it's also been identified with a quotient of Harvey's curve complex. And so Harvey's curve complex is it's also a simplicial complex parameterizing curves on a smooth surface of genus G with n punctures. And then if you quotient out by the action of the pure mapping class group of the surface, then you get delta GN. And similarly, well, or maybe not similarly, delta GN can also be identified with the quotient of Hatcher's sphere system. So the sphere system is a complex parameterizing like spheres inside a particular 3 manifold. And again, you quotient by the action of the mapping class group of the manifold, and then you get delta GN. And delta GN is also, when n equals to 0, delta G is related to the simplicial completion of the outer space defined by Kohler and Voigtman. And so here, and these objects are all from decades ago, or so they are old and well studied objects in math. And in particular, this first identification here allows us to identify the rational homology of delta GN with the top weight cohomology of MGN. And what do I mean by top weight and cohomology? So roughly speaking, the cohomology of MGN carries a mixed Hodge structure, and therefore there is some weight filtration on these homology groups. And so by top weight, we mean, okay, now look at the top graded piece of this filtration, and that's identified with the rational homology of delta GN. And delta and MGN is a very fundamental object in algebraic geometry, but little is known about its topology. So it's highly complicated. And so, but by identifying through this tropical space, new discoveries have been made by, for MGN. And so people have been like pretty excited to look at this tropical space delta GN. And that's also how I got into studying this space. And what do we already know about delta GN? When G goes to 0, back in the 90s, Robinson and Whitehouse studied something called the tree representation, and it can be identified delta 0n. And they proved in their paper that delta 0n is homotopy equivalent to a wedge of spheres. And they further computed the SN representation afforded by the top degree homology induced by the SN action of permuting these n marked points. And Biller, Holmes, and Voltman, they also studied delta 0n, but under a different name. So they were looking at this other space called the space of phallogenetic trees. And these trees are from biology, and they're basically evolutionary trees. And the idea is that, well, if you have some leaf data of species and you know how far apart they are, then how can you reconstruct your evolutionary tree? And the space they came up with to tackle this problem happens to be delta 0n as well. And they were also able to show, so their results coincide with Robinson and Whitehouse because math works. So that's great. And fast forward 20 years, when G goes to 1, Chen, Glacius, and Payne proved in a recent paper that the homotopy type of delta 1n is also a wedge of spheres. And they were able to compute the SN representation afforded by the top degree homology as well. So then one might ask, well, in degree, in genus 2 or higher, are we still gonna observe this homotopy type of a wedge of spheres? Unfortunately, in genus 2, this pattern breaks down. First of all, how do we know it's not homotopy equivalent to a wedge of spheres? First, it has non-trivial homology in top 2 degrees. And secondly, if we look at its integral homology, Chen proved that there's torsion in its integral homology. And so that's pretty sad. And in an earlier paper, Chen was able to compute by computer the rank of the rational homology groups of delta 2n for n up to 8. And in an earlier paper by myself, I computed the SN representation afforded by these homology groups of delta 2n up to n close to 8. And through my earlier project, we kept observing something that relates delta 2n with configuration spaces. And so that's sort of how this curiosity of like, can we make this connection more concrete comes into the picture. And so now I'm gonna tell you what I observed and how we were able to make a connection between delta 2n with a configuration space. So theorem by Chen, Glacius, Payne said there is a large subcomplex called the bridge locus inside the delta GN that's contractible. And the bridge locus contains a lot of combinatorial types that I will not spend too much time on. But in the complement of the bridge locus, we actually see combinatorial types that are genuine genus G graphs with distinct marked points. And by distinct, I mean no 2 marked points are inhabiting the same vertex. And in particular, for genus 2, we get a very simple description for the complement of the bridge locus. And in the complement in genus 2, we actually observe that all the combinatorial types look like some arrangement of points on this theta graph. And for example, we might have a combinatorial type looking like that, or another one looking like this. And these rays are the marked points that we didn't see before. And if we squint our eyes, these almost look like configurations on the theta graph. And however, there is no one-to-one correspondence between tropical curves with configurations on theta, because remember, the tropical moduli space parameterizes isomorphism classes of tropical curves. So whenever you have a graph isomorphism, then the two tropical curves are going to be identified. But then, for example, these two tropical curves, if I just switch the positions of 1 and 2, then these two tropical curves, they're identified to be the same thing, to be the same class in delta 2n. However, considered as configurations on graphs, they would be different. And so that's actually the major difference. And we were able to make this difference concrete, and by giving an isomorphism of Ascendant representations. So basically we're saying, well, you can compute the homology of delta 2n, but what you've got to do is that you've got to look at the configuration spaces of theta, and you need to mod out by the isometry group of your theta. And this plus here is the 1-point compactification of the space. And we have this 1-point compactification because remember, before we had a big contractible subcomplex and we were looking at the complement, and the complement looked like the configuration space. And so to get the entire delta 2n, we have to throw back in that point that we contracted. And so that's how this compactified version comes in. And we also get some other sign representations because of permuting edges, and then you have some permutation action on like R3 and this and that. But that's not as important. The most important part is that we are able to compute the homology of delta 2n through the homology of the compactified configuration spaces on this particular graph. And so now that we are on board, hopefully, with the idea that configuration spaces are relevant, now I'm going to tell you a little bit more of how we compute the homology of these configuration spaces, as well as the SN action on it and the action of the isometry of the graph. And I've been talking about configuration spaces, and here comes the definition. So if X is a topological space, then the nth ordered configuration space of X is X to the n minus the fat diagonal. So the fat diagonal means, look at the n tuple of points. Whenever you have 2 points coincide, then you throw that point out. And intuitively, what this means is that we're putting n particles inside our topological space X, and we're saying no pair can collide. So intuitively, you can just think of like n points running around our graph or any other topological space. So in our case, we want to know what happens when X is a finite connected multigraph. And we want to know how can we characterize the SN action on this space by permuting these labeled particles, as well as how does the isometry of our graph act. And one observation we make is that taking the compactified configuration space is actually a homotopy invariance. And this is an interesting observation, because if you just think about the usual configuration space, then it's actually not homotopy invariant, because imagine you have some configuration like on this K4, 1, 2, 3, say, and now you take a homotopy equivalence to the wedge of circles, and now you have crushed 1 and 2 into the same spot here. So now your 1 and 2, they both live on the central point, and that's not a legal configuration. However, when we compactify our configuration space, what it amounts to is to intuitively, we can understand this added point at infinity as a collection of all such illegal configurations. So we can say, well, we can collide, we can let the points collide, but whenever they collide, we're just gonna throw it to the point at infinity. And because now we have this like waste collector, we are able to make this homotopy invariant because then whenever you have a collection, you just throw it to the point at infinity. And now, before we were asking, how do we do this for every different G? But now, since we know every connected graph is homotopy equivalent to a wedge of spheres, we don't have to look at a bazillion different Gs. We can just look at how to compute the homology of the compactified configuration on the rose graph with G petals. And RG, this is exactly a wedge of G circles. So from now on, I'll mostly be talking about the story with conf(n) of RG compactified.
Sorry, I have another question. So yeah. What these points you put on your graph, the 1, 2, 3, I'm not sure how I understand how they relate to our definition of a configuration space. Because yeah, when I saw the configuration space, like the first thing that went to my head was, so if I take X equal to a copy of R, then the configuration space would be Rn minus the braid arrangement, I think.
Yeah, for sure, totally. So let's just look at this idea. So if we have a copy of R, then and configuration on R, you can either think of it as a subspace of Rn, or you can think of it as a collection of points on this one copy of R. So, right, because giving a point in Rn so that no two coordinates are the same is the same as giving n different points on R.
Yeah. Okay.
Yeah, thank you. Yeah, that's a very good question.
Thank you.
Yeah. So that's why usually I like to think of configuration spaces as different configurations of points on one copy of our whatever space we're looking at. Okay, awesome. So how I'm gonna tackle computations on conf2 of RG is by doing a cellular decomposition. And I will illustrate how the cellular decomposition works just by looking at this very simple small space of arranging 2 points on an R2. And it's rows of 2 petals or like the figure 8 graph. And first of all, we're gonna identify RG minus the central point with a bunch of intervals. So we're saying, okay, if you have a graph, a rose graph, and you remove the central point, then you're left with G arcs. And because in configuration spaces, we don't think about automorphisms or anything. Really, every arc is distinct from the other arcs, and every arc has a direction. And so you can identify each arc with an open interval like I to I plus 1. And in our conf2 R2 case, I'm going to identify R2 minus the central point as the union of 0 to 1 and 1 to 2. So now I want you to consider all configurations on this union of intervals that satisfy the relation that x1 is left of x2, and both of them are on the first interval. So it looks like something like this. And back on the rows, this corresponds to a picture that looks like this. And I claim that this description gives a bunch of configurations, and these configurations are parameterized by the interior of a 2 simplex. So I'm gonna write that down. So these are parameterized by the interior of a 2 simplex. And the reason is that giving a configuration that satisfies this condition here is the same as giving 3 positive numbers, D0, D1, and D2, so that they add up to 1. And on the rows, the 3 distances are here. And so once we sort of fix how the points are related to each other and which arcs they're on, then that defines a cell, basically. And so that's how our cells are going to come from. So now I've just told you the interior of the cell. Let's look at what happens on the boundary. And on the boundary, let's consider first what happens when D0 equals to 0. Well, when D0 equals to 0, then this point x1 is just gonna slide and fall onto the central point V. And on the collection of intervals, it looks like an arrangement or a configuration of just one point, that's x2. And when D1 equals to 0, well, that corresponds to the scenario when x1 and x2 collide with each other. And earlier we said whenever points collide, we're going to throw that configuration to the point of infinity. And so I'm just going to write infinity here. So basically we don't think about it. And when D2 equals to 0, it's similar to when D0 equals to 0. We have the point x2 sliding and falling onto the central point. And if we look at the intervals, then it's an arrangement of just one point, x1. And so from this discussion, we can sort of see the cells on the space conf n RG is gonna be given by configurations of how, or are gonna given by relations of how points, are with each other and which arcs they're on. And there are only gonna be cells in 2 dimensions, in dimension n and n-1, because whenever you have a point sliding down, either it goes to the central point V, but in that case, if you have another point sliding down to V, then they're colliding at V, and so you're really throwing that configuration to infinity. So your degree 0 chains or cells, they're really going to be either arrangement of n points on this collection of intervals or an arrangement of n-1 points on this collection of intervals. So to make that more formal, I'm going to say an n cell is given by a pair of functions, sigma and chi, where sigma is a permutation on n. So this is the situation when we have all n points on the arcs, so nobody is at the central vertex. And this sigma is going to tell me, looking from left to right on my collection of intervals, how are these points gonna stand in a row? And secondly, I have this step function chi. It's a non-decreasing function, which means I'm looking at how am I distributing these points to each arc. And those 2 are the only 2 pieces of information you need to know to define a cell. And now we can try to write out all 2 cells of our conv2 R2. Well, they're going to be given by the descriptions. You have 1 and 2. So I'm going to use a bar to mean, I guess, a different arc. So you have 1 left to 2, and both on the first arc, and that's it. Or you can have 2 and 1 on the first arc, or you can have 1 on the first arc, 2 on the second arc, or the other way around. Or you can have nobody on the first arc and you can have 1 left to 2 on the second arc or the other way around. And so these are all the 2 cells of our conf2 R2. And so say we just take this one, and on the rows, so wait, which way are my rows going? Okay, so so this is my rows, and this corresponds to the configuration that we have 2 and 1 on the left on the first petal. And similarly, an n-1 cell also have a description like this, except that now we're really taking an injection of n-1 into n, and the missing number in the target tells us which point is now inhabiting the central vertex. And we're gonna have a similar step function that tells us, well, how many points per arc. And so all the 1 cells of conf2 R2 is gonna be 1 bar. So this is when 2 is at the central vertex, or 2 bar, and bar 1, and bar 2. And so if we take this one and look at how it looks on the rows, then it corresponds to the configuration with 2 on the second arc and 1 on the central point. And this is going to be our cellular decomposition. And it's a pretty, it's a very short decomposition, but that's good, because that means when we compute homology, we're just gonna get 1 homology, or two homologies. Okay.
I had another question.
Yeah.
So you mentioned on the previous slide that, if our cell is inside, one of these intervals, you get a simplex, and then you kind of have to treat the boundary special, but it's just in the interior of a simplex. Yeah. It feels like you have to be more careful if your cell has like X1 on one interval and X2 on the other, because there are
for sure
invalid distances between those two.
Yeah, no, totally. That's an awesome observation. Thank you for raising it. So when we have 1 point on one arc and 1 point on another arc, instead of getting a simplex, we're actually getting a product of 2 simplices. And because, let's just look at this one, then the space parameterizing having point 2 on arc 1 is the interior of delta 1, and similarly for the other one. And so the cell that parameterizes this configuration is going to be an open square. And similarly, if you have more arcs and more points, you're just gonna get a product of open simplices of different dimensions, and the dimension depends on how many particles you have on that arc.
Okay, thank you.
Yeah, that's a really good question. Okay, so here are our cells. And once so some of these cells currently, I guess I've been sort of describing these cells in conf2 R2. And so some of them appear to be open cells. But once we throw in that point of infinity, all these cells are gonna be closed, and they'll be like nice and good to go. Okay. So now we have all these configurations and all these descriptions for the cells, and we see that there is a natural ascendant action on the cells by simply permuting the labels. And a footnote is that we actually used a slightly different basis that's a lot worse, and I don't know why we aren't using just permuting labels, but they're equivalent, and I think it's a lot more intuitive to just think about the cells as being labeled by, the configurations I just gave you, and think of the ascendant action as just permuting the labels. And if we take this action to be our ascendant action, then we see that the action is free, because Well, because permutations on Sn, it's the permutation action is free. If you have Sn and you ask another permutation to act on your elements of Sn, then that's a free action. And if you have an n-1, a set of cardinality n-1, so since the smallest permutation you can do is a transposition, but if you already have n-1 points, then nobody fixes your. Does that make sense? Sorry, I feel like I lost it a little bit, but the idea is that if you have an arrangement of n-1 numbers and you let an Sn permutation act on your n-1 subset of n bracket, then that action is still free. So that's the whole point. And since we have the free action, we can just represent each Sn orbit of these n cells by taking the first function information to be the identity for n cells, or just inclusion of n-1 into bracket into n bracket for n-1 cells. And each orbit is gonna be labeled by a step function.
Wait, sorry, Claudia, can you say again the thing you said about the free action? So you have Sn acting on a set on n, like a set of 1 through n.
So imagine you have
and then
1, 3, 4 as a subset of 1, 2, 3, 4. And then you look at Sn S4 acting on 1, 3, 4 as a subset of S4. Then this action is free.
So you just define like anything that moves the like how would 1, 2 in S4 so act on that set?
Yeah, it's just gonna give you 2, 3, 4.
So it really is acting on subsets of size 3.
Sorry. It doesn't
of 4. Okay.
Yeah, totally. Sorry. Yeah, it doesn't act on this particular subset, but it acts on all n-1 subsets of n bracket, and this action is free.
Got it. Thank you.
Okay. Thanks for the question.
And I think that makes sense with the configuration picture, because you've got like the x2 vertex is still there at the center of your rows, and so you're just swapping the x1 vertex and the x2 vertex in your picture.
Yeah, exactly. It's all, you just have all these configurations, and then it's not like, so in this case, like Mark said, it's not like your point 2 is missing. It's just missing from the arcs, but the 2 is still at the center, and so S4 still acts on this configuration. But now it's just sending 1 to the central point, so you don't see it on the collection of intervals. Okay, awesome. So now, if we're counting Sn orbits of these cells, now this is a combinatorics question for our combinatorialists. In degree k, and k could be n or n-1, then the number of step functions, of non-decreasing step functions, like what's this number? Well, it's the number of ways to place g-1 bars in a row of k identical beats. Right, because you're really just saying, okay, I'm gonna put this many beats on arc 1, this many beats on arc 2, this many beats on arc 3, and this number comes down to n plus g-1 truth g-1 in the case of having n particles on your interval, or n plus g-2 truth g-1 when you have a point occupying the central vertex. And it is a theorem that the Sn equivariant cellular chain complex that computes the homology of this guy here as an Sn representation is this chain complex here. And I haven't really told you what is this differential here, but this differential is exactly going to be what we said earlier of how when you take one distance to be 0, then you basically slide your particle around and move it to the central point. And it's exactly going to be that modulo some sign, crap. And one thing that was really frustrating about this project is how many signs it involves. And you have to be like really careful with how you embed everything, how you define the signs, and when you have an action, how are you like permuting the signs? It's horrible. But I will give you an example of this chain complex in a minute. So now let's just apply what we just learned and look at conf2 R2 plus. And let's see, so we have n plus g minus 1 choose g minus 1 for the first number here. And when n and g are both 2, then this is equal to 3. And similarly, n plus g minus 2 choose g minus 1. That's 2 choose 1, which is going to be 2. And so our chain complex is just going to be z as 2 to 3 copies and to z as 2 squared. And I'm going to order, so now the S2 orbits, they're really just labeled by step functions, right? And I'm going to label the order the S2 orbits by in this order, just because I'm going to write the matrix of this delta for you. And so I'm going to label the S2 orbits in this order and label the S2 orbits in the degree 2 chain complex in this order. And now let's just look at how we can compute this delta. So when we have 1, 2 bar, so that's when we have 1 and 2 on the first arc. And it turns out, so this is delta of this is equal to, I'm gonna leave the sign blank for now, is gonna be removing 1 because 1 had slided down to the central vertex and left 2 here, plus some sign of, now if 1 and 2 collide, then that goes to a lower, that just goes to the degree 0 chain, and so we don't think about it. And if 2 slides down to the vertex, then we end up with this configuration here. And it turns out after some careful manipulation that we always get plus for the case when the left vertex, the left particle slides down, and we always get minus for when the rightmost particle slides down. And in our notation as z as 2 modules, we can write del of 1, 2 bar, or sorry, yeah, equals to, so this is gonna be 2 bar minus 1 bar, or as permutations of the identity. So this is going to be 1, 2 minus the identity, which I'm going to write as 1. So, and this 1, 2 here, we can just write it as 1 as a permutation. So one confusing point is that when we are writing this matrix, the matrix for the differential, the entries are going to be elements of ZS2. And so the entries are going to be permutations. And the bases for these two are exactly these two that I wrote here. And similarly, we have, if we are looking at del of 1 bar 2, then that's going to be sliding 1, to the left, minus sliding 1 to the right, but then those are the same thing, plus sliding 2 to the left, minus sliding 2 to the right. And so we're going to get 0. So this is bar 2 minus bar 2 for the first arc, plus 1 bar minus 1 bar for the second arc. And finally, del of bar 1, 2 is going to be bar 2 minus bar 1. And in permutation notation, this is going to be 1, 2 minus 1 again. And so as a matrix, this matrix is going to be 1, 2 minus 1, 0. So this is the first column, 0, 0, and 0, 1, 2 minus 1. And what does this mean? So this means you have 1, 2 minus 1 with the step function that you have something bar. So that's what being in the first row means. And 0 just means, well, you are not getting any configuration that looks like bar something. And in the second column, we're saying, well, if you have something bar something, well, you just never get anything at all. And in the third column, if you have bar 1, 2, then you don't get any configuration in the boundary that looks like something bar. But you do get a configuration that looks like bar something. And in particular, if we consider the permutation of bar something, if we consider what's the permutation that gives us this, then is 1, 2 minus 1. So I think this part is a little bit weird. But does it sort of make sense? Yeah. The idea is really that we have 3 copies of step functions, and each basis is identity plus that step function. And so we're just looking at how do we how del acts on the identity. And anyways, I think I will maybe stop pushing y'all to understand this, but basically we get such a matrix for every conf and RG plus, and this matrix is we're putting it in the drawer so we can calculate it later. And I see I'm running low on time, so maybe I won't go as into detail for this part. But so we just now studied the Ascendant action on our homology of configuration spaces. But remember, before we also had another action of the isometry group of the graph. And how are we gonna characterize that in terms of something acting on the configuration spaces of RG? Well, it turned out that the correct group to consider is out of G, which is the group of outer automorphisms of the free group on G generators. So by definition, it's the group of all automorphisms modeled by the inner automorphisms of FG. And the inner automorphisms are all the automorphisms induced by taking conjugations or by sandwiching your element in conjugation. And we can see how out of FG act on conf and RG plus. So because pi1 of RG is the free group on G generators, so since each circle in your wedge is going to contribute a generator, so the automorphism group of RG is going to be all the self-homotopy equivalences on RG and modeled by based homotopy. And by based homotopy, I mean this V is going to be fixed for the entire time. And now if we're considering out FG, then we're taking all the self-homotopies and we're saying, okay, 2 homotopies are the same if they are the same up to free homotopy. And that means that we no longer require this V to be fixed the whole time. And then because conf G, because taking the compactified configuration spaces is homotopy invariant, we get an out of G action on the homology, on this space, and therefore also on its homology. And the reason why we need out of G is because when we take a group isometry, basically it comes down to that sometimes your chosen base point is not necessarily staying still for the duration, and so you could have your base point moving around, and so there is no. So really, okay, we want to embed the isometry group into one of these groups, but there is no embedding of the isometry group of your graph into out of G, because it's not guaranteed that the base point is fixed the whole time. And so really it's out of G that we should be considering. And so now let's look at how we can compute this out of G action.
Claudia, just heads up, probably, well, I want to give time for questions. So
okay.
We finish at 2 and leave a few minutes for questions.
Gotcha,
so
gotcha.
I guess work backwards from that.
Okay. Okay, so basically the idea is that out of G is actually generated by particular elements. And even though out of G doesn't act on the chains, because the action of out of G is kind of like up to homotopy, but your configurations, they're not up to homotopy. If you up to homotopy, then you get different configurations. But we can realize this action by automorphisms of RG to RG. And because we already have a chain complex from before, now we can just take a set of generators of out of G and realize those elements by continuous maps from RG back to itself. And that gives us an action of a configuration to another configuration. And so that's how we obtain the out of G action on our chains. And we have like a little trick of how to compute things faster, but I think that's not super important, so I'm gonna pass. And so now basically we have this as an action, and we know how to characterize the action of the isometry group of G. And we can actually now tie this loose end back into tropical geometry and compute the homology representation of delta 2n. And we were able to perform this computation for n equals to 10, and we get particular multiplicities of irreducible representations for up to n equals to 17. And it's pretty cool. And we have a GitHub page that you can look up all these data and stuff. And because of our data, we were able to make a conjecture that's about the multiplicity of some particular irreducibles. And we suspect that these numbers, like they look like they are related to the dimension of the space of cusp forms. And I don't even know what they are, but they're like modular forms and like super fancy. And so hopefully someone or us will prove this one day. And finally, thank you for your attention and all the wonderful questions.
Awesome. Let's get a round of applause. That's a great talk. All right. Do people have questions for Claudia? Okay, I have a question.
Okay.
Okay, so I guess, so I'm coming from the perspective of like knowing about the White House representation, like that zero, the genus 0 case. And so like there's a lot of things about that representation that like are interesting.
Yeah,
so,
I
like,
totally agree.
So like for one, you could restrict that representation to Lie.
Yeah.
And like there's a nice like character, like Lee has like all these like things that are really nice, like, you know, like you can have a formula for the induced representation, or like it restricts to the regular representation, or like it's isomorphic to the like top homology of the partition lattice. Like all these
I
things.
love this part of the story.
Right. So I guess I'm wondering, my first question is like, have you been able to like any of the representation theory, have you been able to relate it at all to like that G=0 case?
I that's when I disappoint you. No. I think I would love to see more connection. And in particular, I guess I have this vision that, okay, so I have a previous paper where also about delta 2n. I've just been looking at this like theta graph for 3 years now. And but in my other computation, you could actually look at which graphs contribute to homology classes. And so I have this vision that, okay, maybe we could look at, you know, which graphs contribute to the homology classes and see if there's any interesting combinatorics there, and like kind of like generalize that combinatorics. But I guess that's just like still an idea, and haven't been able to like find anything interesting. Like right now it's all like very messy, and you get like a sum of, I don't know, 20 graphs, and then that's your homology class. And it doesn't feel very illuminating. Yeah.
I guess like to me, like when you were describing the N cells, it felt a lot like composition, or I mean it was like compositions, kind of like weird compositions of N, and it felt like there should be some sort of like relationship to the partition lattice and its homology, or somehow like some map between them that relates them.
Totally. Can I tell you some like things I just haven't told anybody?
So yeah, we are recording, so I don't know if you want to stop the recording.
No, it's not a secret, but basically we have this other idea of computing you know, these homologies of configurations. For example, just the theta graph, we want to give it a filtration by the partition lattice. So basically you can look at, I think that's one technique people in the configuration spaces use a lot. So you look at, you know, the n-fold Cartesian product, and then you can give it a filtration by requiring, okay, so which blocks of points are colliding. And then your configuration space is going to be the open stratum at the bottom when nothing is colliding. And there is a recent paper, well, not so recent, in 2016-ish, by Dan Peterson, where he wrote or discovered the spectral sequence. Then you can like sort of use with a filtration or like a stratification of a space. And basically you can use data, or you can use things you know about the closed strata to compute things about the open stratum. And in configuration spaces, it's like always easier to compute anything about the closed stratum, because you just get, you know, your space to some power, and that's always going to be your closed stratum. And so then the homology of the open stratum is controlled, you know, by the closed strata, as well as the the combinatorics of the partition lattice. And so, but yeah, so yes, there is a lot of connection there, and right now we're trying to just study the spectral sequence and see what we can learn about, or like if we can have a conjecture, say for the dimension even of the top degree homology of the delta 2n. And it's work in progress, and I'm really excited about that.
Well, I actually have more questions, but I want to like give people a chance, other people to ask questions, and or to leave if they have things to do. So yeah, does anyone else have questions for Claudia?
I think I managed to get all my questions during the presentation itself.
Okay, let's give her a round of applause, and then maybe we can stop the recording and I can ask my other questions.